So students, can you see my slides? Somebody?
Yes, sir. Yes, sir.
Okay, so let's get started. Okay, so today we'll start a new discussion. This will be on the fabrication of nanomaterials, means how we make nanomaterials. So different processes, procedures, right? So I already mentioned to you that there are two ways of generic ways of doing it, of making nanomaterials. One is called top-down process and the other one is called bottom-up process, depending on whether we start with a bigger chunk of material and break it down, or we start with atoms and build it up, right? So these are the two possibilities, top-down and bottom-up. So we will go through both of these, right? But I don't know if towards the end of the semester you guys can come into the campus, then I will demonstrate a little bit of bottom up to you in the lab. Okay. All right. I already told you that we had been learning from nature, and nature has been, making nanomaterials for billions of years now. And nature does it, of course, in the bottom up, mostly in the bottom up, but also some processes like say volcanic eruption, that is also a natural process, and volcanic eruption also results in releasing some nanoparticles in the atmosphere. Okay, so nature is doing both top down as well as bottom up, but most of the processes are bottom up. Now you see this beautiful blue butterfly. Okay, now typically when we see a beautiful color, we obviously relate that to the presence of some dyes, some coloring pigments, something there that is colorful. Okay, that means when we see a beautiful blue butterfly, we get a feeling that there is something there on the surface of the leaf that is blue in color. Okay, but honestly speaking, that is not the fact. Like this butterfly, I zoom in onto the wing, okay, of the butterfly. Now this is a scanning electron image. Okay, we call it as a micrograph, a scanning electron micrograph, and you see the scale bar here, that is 1 micrometer. Okay, that means 1 millionth of a meter. Okay, so it's extremely small. This, to see this, you are magnifying about 15,000 times. Okay, and then you see some structures like this on the surface of the leaf, on the surface of the wing. Okay, the butterfly wing. Now it is because of these structures here. These are because you see this is 1 micrometer. Now this will be about 100 nanometers. So you see these small rods coming out like this. These are typically about 50 to 100 nanometers. Now what is happening here is that the blue color that you see is more like an optical, you can say, event or a happening, something like the sky. The sky is blue, we all know, when we look from the earth. Most of the time we see it blue, right? But it is not blue, right? And if you take a plane, go up, you won't see the blue sky. Now what is happening here is that the dust particles that are there on, in the atmosphere, they actually play around with the light coming from the sun, right? And a process called diffraction, diffraction, diffraction happens. And when light actually grazes over very pointed structures, then what happens? The light spreads out. That means spreads out in the sense that there is a bending of the light. Okay, as it grazes over a very pointed surface, it changes its direction. And the change in the direction depends upon the wavelength of light. That means how much amount of change in the direction the angular change, what is happening is depending on lambda. Lambda is the wavelength of light. And a visible light or white light is composed of many components, right? We call it VIBG, or violet, indigo, blue, green, yellow, orange, and red, right? These are the basically visible, you can say, parts of the spectrum. All these mixed together, you are getting it white light. But all of these are different wavelengths. And that's why when light grazes over it, there is a change in the direction of the light based on the wavelength. And for the light on the diffracting on the dust particles in the atmosphere, it is the blue light that actually comes down to us. All right, the other, because there's a dominant color blue, and it comes down towards Earth, and that is what we see. As simple as that. Exactly similar phenomenon here happens here. These are what we call as sort of like diffraction gratings. Okay, when we have repeated structures, one following the other at a almost similar distances, spacings, then we call that as a grating, right? So a typical optical instrument, if you use and you want to use it for different wavelengths, it will also have a lot of gratings like this, right? So very similar. These are naturally made gratings, and as light passes over it, white light, they again go through diffraction and different colors spread out, and the blue color basically comes to the eye and we see it blue. So this is a example of, again, a variation in optical properties based on the nanometric surfaces. All right, so basically this is what we call as a surface structuring that is done by nature. Okay, so this is a typical example of natural nanomaterial. What is this? This is a gecko or a lizard. Okay, so many different variants of lizards are there. And it's so common to see that lizards are moving around on the walls, even the ceiling. You have observed, right? Lizards can walk upside down on the ceiling. Okay, so how do they do that? So that is something, I don't know if you ever thought about it, that can they, just move around upside down? Why don't they fall down? Now this is because of the unique structure of the legs, okay, the feet, basically the fingers that they have. Okay, this is the bottom view of a gecko feet. Now let me zoom in. Okay, let me zoom in into these. What do I see? Okay, that is it. That is a zoom part of this. This stretch is going right. This is the one. And if you see, if you look here, these are very, very small cups. Okay, very, very small cup-like structures. These hangers that we use in the toilet sometime, the air, we press out the air and they stick immediately, right? The cup-like structures. The same concept here. These are basically small, small cups in nanometric sizes, and there's billions of them. Not one, two, it's billions of them on the feet of these gecko. And that's why they press, and automatically the air inside the cup goes out and it sticks. All right? So the same concept, again, another example of nanostructures made by nature. Okay?
Sir, hello, sir.
Yes?
Hello.
Yes?
Sir, can you repeat once again this gecko concept?
Sure. Let me go back. Yeah. So this is the maximum image I could find. You see all those small, small things there. These are like cups, small cups. Okay. Now, the example that I gave you of the fittings in the toilet, sometimes we use that, right? The hangers, the small, small hooks. So if you have a cup at the plastic cup at the base, soft plastic cup, and if you hold it against the wall and press it, then what happens? The air inside goes in and it automatically locks in. You know that, right? Maybe I'll send you a picture or two of those cups also that are there. So what happens is, these type of small, small cups, there are billions of them on the feet of a gecko. So when the gecko walks, all right, it presses against those and automatically the small amount of air inside those cups, they move out, and the locking, we call it as the airlock, happens, and it gets stuck to the surface. And if you can open it only by sliding, if you try to pull it down away from the surface, it won't come up. Okay, then you slightly slide, then again air moves in, and then you can release it. Okay, so that is basically the technique. Let me quickly see if I can find one. Just a minute. Let me see if I can show you an image. Let me go to Google. Let's see if we call as air cups. Images. Toilet hangers. Air cup. You see all those? These are the pictures. Can you see them? Can you see my screen?
Yes, sir.
Yeah, you see all those, right? So these are the things. The cup-like thing, if you press, it sticks. Then if you slide, it comes off. Okay, all those. So the same concept there. Anyway, let me go back to the slides. Now, this is another example of natural nanomaterial or nanostructuring of a surface. Now, this is a typical lotus leaf. Okay, some plants like lotus, then yam. All right, you see that water doesn't spread on them. They form droplets. And lotus leaf is known to be the cleanest surface made by nature. Now, how is it so clean? It is because, as you see here, the water does not stay. Okay, it forms bubbles, and the bubbles roll off. As the leaf moves here and there, the bubbles roll off. And when they roll off, they carry all the dust particles along with it, and that's how this is clean. But what is it? Why it does not spread out like other leaves? Why this particular leaf, the water does not spread out? Let's look clearly now, closely. Now I'm zooming in here. You see the scale bar here? It is 20 micrometers. That means this is basically half of your hair. That means if I put a hair here, it would be roughly like this, right? Because minimum 50 micrometer is a hair diameter. So you see these are very small. Okay, if you take take a typical hair on the end tip, you can at least have a few of them sitting there, this type of structures, but they are still in micrometers, right? Because this is 20 micrometers, so this will be roughly about maybe 10 or 15 micrometers, and the tip will be in nanometers. Okay, so what happens, all these structures are there, and if you zoom in this particular one, I don't know if I couldn't find an image, but if you zoom in here, I have a picture to show you. I should have one. Well, unfortunately I don't have, but what you see here, these mounds, they are like hair-like structures all over. You see there are small hairs on these, and these hairs are very small. They are in nanometric sizes. Okay, maybe 10 to 20 nanometers in diameters or even less, and there are many of them jutting out. So what happens when you drop water, because I did a very systematic study on what we call as super hydrophobic surfaces. Hydrophobic, you know, hydro means water, phobic means afraid of, right? Phobia. So anything that is afraid of, or water is afraid of, if you say, they are called hydrophobic surfaces. So hydrophobic surfaces will repel water. They will not allow water to stick on it. So what happens is, because this is a huge water droplet, if I put it here, it will be very big. So what happens, because of these small structures jutting out, the weight is distributed on these small tips all over from the weight of this water droplet. And my personal study shows that if this water droplets sits on surface which is less than 40% of the surface area at the base of this water droplet, then the water droplet does not break open. It retains all the surface energy to keep it as a water droplet like this. And that's precisely why these type of surfaces, they don't allow the water droplet to spread out, and then you see some tilting, then the water droplet will roll off and it will carry all the dust particles with it. Now this is another example of a typical nanostructuring done by nature. Now during a part of my research team, they are actually working on what we call as self-cleaning surfaces. The team I had in Bangkok and again in Don Bosco University, there are a couple of students who actually were working on these self-cleaning structures. And you think about it, this self-cleaning concept can be put on buildings because some of this material that we use can be transparent also. So if this is transparent and you put it on big windows, you've seen those huge, high-rise buildings, right? You won't see too many here in the Northeast. Go up to Delhi, Bombay, New York City. New York City, you basically have to lie down on the pavement to see the top of the buildings, like 120 stories. So think about how difficult it is to clean the glass, because most of the buildings use glass outside. And wouldn't it be wonderful if the glass always keeps itself clean? It doesn't ever get dirty. Okay, so people are working on it now. Such type of glass actually has come out. Even not only glass, any surface. Mercedes-Benz has a model where you don't have to clean the car because the car never gets dirty. This is again because of some type of structuring like this on the surface. And in fact, you cannot scratch. Do you know? Mercedes-Benz, you cannot scratch the paint away. So those are interesting things. I'll tell you. I'll show you some pictures also of the different products where nanomaterials are being used. Now, see, we're trying to mimic nature, right? We are trying to see if we can do the same thing that nature has been doing for billions of years. And that's why we tried to make some structuring that will sort of resemble this. And you see this image here. This is a picture I had taken personally using a scanning electron microscope from one of my work. So here also we were trying to spread the surface area like this. Okay, because if I put a water droplet here, you see it won't, there are a lot of vacant spaces. They will be touching this, maybe this, but there are so many other spaces where this is vacant. And you see the scale bar, this is 1 micrometer. So these rods are roughly about 500 nanometers, okay, in the diameter range. And then we did some studies on these. So we try to see what type of what happens when we put water droplets. Now you see this here. This is again a picture, a photograph I had taken with a machine that I designed myself. Okay, so this machine, just a minute. This Google class এটা লৈ আছো, মই কল বেক কৰি আছো ক্লাছটো হলে। ঠিক আছে, মই ক্লাছটো হলে কল কৰি আছো। All right, so this is an optical microscope. Okay, the photograph is optical. This is not a scanning electron microscope. Otherwise, you won't see the color. So you see greenish thing here. That is a lotus leaf. So what I did, I took a lotus leaf and put a water droplet there. Okay, and these are some measurements we do, what we call as water contact angle. I won't discuss this now because it's outside the requirement of this course. But basically, this angle that you see here, bigger is the angle, more the surface is super hydrophobic. Okay, so a typical lotus leaf, this angle is about 150 to 160 degrees, right? And then using the same instrument that I designed, we took photographs of water droplets on type of surfaces like this. You see here, this is a surface that we developed with this type of rods on surface, and you see the water droplet was close to 150 degrees, very similar to the lotus leaf. And just to make sure that these rods are playing the role, this base material that I used for this experiment was what you call as this bandage, bandage that is used to pull in blood. It's a super hydrophilic surface. It loves water. Bandage, the moment you put in, it pulls in all the blood, right? So same thing, it's a bandage where it was supposed to pull in all this water, but just because we did some structuring like this, it has become a super hydrophilic surface. It started hating water. Okay, so you see what nature has been doing, it is also possible that we can try to do it. And this process, again, when I made all this material, it was simple bottom-up process. That means I started with atoms to put the atoms together to make structures like this. Okay, I'll come to details of how we do that later. But I was just showing that what nature has been doing, we can also sort of try to replicate with whatever facilities we have. So I mentioned all these, that natural activities can actually uh, generate a lot of nanomaterials in the atmosphere, like this volcanic eruption, even high tide, okay, tsunami. All these things can generate very, very small particles in the atmosphere, typically below 100 nanometer in diameter. And the same thing we can do in a lab. Okay, we can make these particles in a lab, and it's also industrial emissions that also carry a lot of these small carbon nanoparticles. Okay, so there's various ways that nanoparticles can land up in the air, uh, which which may be dangerous, of course, but nature has been doing it. Okay, and our body is immune to all this, but then too much exposure may create some problems. Okay, let me check if anybody's waiting. No, I think all of you can get in, right? How many? Only 18 students. Okay. All right, let's continue. So, uh, let's now discuss step by step how we human beings can make nanomaterials, right? And I already mentioned the generic processes. So let's pick up top-down process first. There are so many different techniques that can be adopted uh, in the top-down process. It's not a typical hammer that is hammering, right? But the idea is that we use force, we use energy, we use force to make nanoparticles from bigger chunks of the material. And this can be physical force, that is mechanical force, or it can be even heat. Okay, we can heat up. Okay, and then we can break materials, we can convert them into gaseous forms and all those, and then we can get some nano materials. Okay, so I have put down in a tabular form some of the typical processes or techniques that can be adopted to make nanoparticles. Now these are very, very small descriptions, because if you have to go to detailed description of each of the techniques, then it will be like a humongous job. It will be huge. It is not possible in a one semester course. But of course, you should get to know an idea of what are the different types or processes that can be adopted to make nano particles. So ball milling is one technique where actually we use some metallic balls too, and the balls are made to roll over this material, and as it rolls over, even the container rolls. The container rolls, and inside the container there are balls that roll. I think I have a picture. Oh, yeah, this is it. See, so basically you'll have a spherical container which is moving. See all these rollers here, that means the ball is also moving, and inside there the smaller balls are moving around, and this is the material, and as it keeps on happening, moving, it starts breaking this up. Okay, and we get sort of uh, particles, not very consistent in shape because it keeps on breaking. So we cannot say that by ball milling we will get very, very spherical particles, or we get square particles, or we get cubic particles. No, it may be of different shapes, but the size can be taken down to nanometric levels, less than 100 nanometers at least. Okay, so this is the ball milling technique that can be adopted. This is not a very expensive technique, but like I said, it is not a consistent technique. That means you get a wide range of sizes, and you get a wide range of shapes also. Okay, then another way we can talk about is rolling, beating. All right, you can just beat. Beat means, apply mechanical pressure, but to take it to the nanometric size, the material also has to have a lot of tensile strength, otherwise it will break, right? say typically gold, you can beat it, beat, and it becomes very flat, thin surfaces. A typical two-dimensional nano structure can be made. That means one dimension can be very thin sheet. Okay, I think I should have something to, yeah. So basically something like this that you see here, breaking, beating, and then you can even go to what you see here, very small. So these are all atoms. Okay, one single layer of atom can be done, and you can roll, you can make them into various forms. Okay, so that's about rolling and beating. Another process of making nanofibers means, again, you'll say a one-dimensional structure. That means it is long in one dimension, the other two dimensions are very small. Okay, it's like a hair. If you take a hair, then in one dimension the hair is very long, right? But in the other two, if you look at the cross section, you'll see it's very small, you cannot even properly see, right? Something similar to that when we talk about extrusion or drawing. Okay, so we can draw out very thin fibers. Okay, and the thickness or the width of this diameter of these fibers will be in nanometric sizes, but the length will be long. Okay, maybe millimeters, maybe even centimeters. Okay, so that's quite long as compared to the diameter. I don't know if I have a figure of that. Yeah, see, this is one process of doing. This is an extrusion process, and these are the magnified image, of course. So all these wire-like things coming out, the diameter will be a few tens or hundreds of nanometers, but the length is more. Okay, and they can be used for various applications. So we'll talk about the application thing later, but this is how we can make, okay, nano-sized fibers. Nano-sized, when we talk about fibers, we automatically mean that it is a one-dimensional structure, nanostructure with one dimension very long. Okay, and that's why we call it as a fiber. The other dimensions are small. Okay, so here the long dimension is this one, the other dimensions will be the x and y of the surface, right? So x, y, and z we call it. So x, y will be at the surface, and z is this one, suppose, right? So z is long here, the other two are within nanometric sizes. That means they follow what we call as the not the classical mechanics or classical physics, but what we call it as, anybody? What do nanomaterials follow? Hmm? Can anybody tell me? It's quantum mechanics or quantum physics. Okay, we already mentioned it. So if you talk about this nanofiber, it's classical mechanics of classical physics along this direction, but along this direction, it is quantum. Okay. If you find it very difficult, stop me any moment. Okay. The idea is to don't take it like it's very difficult thing that I'm talking to you. Try to look at it in a very simple way. I hope you understand that we are pulling something. We are making small fibers. Okay, and we keep on pulling, then obviously the length will go on increasing and increasing, and as the length goes on increasing and increasing, the diameter goes on decreasing and decreasing, because the material volume is the same, right? The amount is same, the mass is same, but you are stretching in one direction and automatically you are making the other dimensions smaller. Okay, that's how we do it. That is extrusion drawing. Then mechanical machining, polishing, grinding, and ultra microtome. All right, these are different again processes which can take materials to sort of micro sizes or nano sizes. You know the processes, right? Machining means using a machine to cut it small. Okay, and mechanical, obviously because of the movement. Polishing, you already know. Use a rough surface to keep on moving over a sample. Okay, that is polishing. Okay, grinding is the same concept as a mixer grinder you have at home, right? A blade keeps on rotating at a very high speed, and your materials keeps on getting smaller and smaller. Okay, similar processes. Ultramicrotome is a technique that you can use to slice material, right, into very thin sizes. And when you're slicing, again, you're talking of a two-dimensional material. It's a thin film, right? You slice something very thin, then the very thin part is actually the nano part. The other part will be bigger, and that's why you will have two dimensions quite big. Okay, so these are two-dimensional nanomaterials, right? So let me see if I have something there. Yeah, this is typical ultramicrotome. Okay, it's a machine and it can slice very thin. Okay, normally uses diamond cutters, very sharp diamond cutters. Okay, then compaction consolidation. Okay, again, it's a process of powdering. Okay, very similar to what we're talking here, ball milling. Okay, so basically powdering. So, compaction is basically, have to, what you can say, the same process of moving around, and then you can have very small particles that can actually coalesce and become bigger particles also. All right. So that's why, you might have very small particles of 2 nanometer, 3 nanometer that can actually coalesce to make 20 nanometers. So, even though 20 nanometer is still a nanomaterial, you might say that it might not be bottom up. Okay, because of the process of using original bigger material to start with. Okay, atomization is another way. When I say atomization, what comes to your mind? I think the sprays that you use. All right, the perfume, nowadays your hand sanitizers. Okay, the spray, that mist type of thing forms, not the water droplet coming out. Okay, there are two different types of sanitizers you use. One where actually the alcohol pops out onto your hand, like you use for liquid soap, and otherwise it sprays it out, right? And it does that by applying high pressure on a very small nozzle, a very small hole, okay, through which the liquid comes out. Actually, it is in liquid form, but when you spray it, it appears to be in gaseous form. Okay, so those are actually liquid itself. It's not gas; it's still liquid, but the water droplets or whatever liquid you are spraying out is very, very small. It's so small that it appears to be floating rather than dropping down. Okay, so those are called aerosols. So atomization is a technique. The water droplets that move out are called aerosols, right? So that way also we can think about making small particles by forcing them through a nozzle at a high pressure. Okay, continuing with the other processes, so many of them. All right. But I don't want to frighten you with all these processes. But if you go through once at least, you will get to know the way this is done. Okay, say annealing, I told that we can use pressure, we can use mechanical force, and we can use even heat, like the previous table that I showed you. This is like mechanical energy fabrication methods, right? All force applied with a lot of other machines to support you, or machines rather, or surfaces to support you, like the balls or the flat plates, mechanical grinders, ultramicrotome. These are different, you can say, tools that you're using for mechanical fabrication. And this one that I'm showing you now, this is thermal fabrication. That means heat. We are applying heat. All right. So annealing is one process. That means putting a very high temperature. Okay. So one way, there are two different ways of doing it. One way, to bulk materials to form nanocrystals. Okay. So you anneal a bulk material at a very high temperature. Okay. Then you might end up getting nanocrystallites. That means nanocrystals, very, very small crystals. And the second is the transformation of nanomaterials into another physical phase. That means if we have a solid, it may move to a vapor phase, right? That's a change in phase, no? There are three phases, solid, liquid, and gases. So it can move from one phase to the other during the process, all right? And you end up with some nanomaterials. Chill block belt spinning, okay, then this is like using a radio frequency coil to force metal, okay, melted metal at a high temperature. Because to melt metal you need high temperature, right? So at a high temperature you have molten metal, then it is spread out through a nozzle and it immediately cools down on a drum. okay, cools down on a drum, and that's why it spreads out like thin wires because the drum is rotating and this is falling and spreading out, and then you end up with some nanofibers. Let me see if I have a picture of that. Yeah, this is the chill block melt spinning, see? So we are having this wheel going at a very high speed, okay? This is the metallic melt. That means the molten metal coming here, falling on this one, okay? And this is very cold, all right? And you see here now, all this being thrown away, and these end up as long fibers with nanometric diameters, okay? So this is one way of making nanofibers. This is another process. We call it electrohydrodynamic atomization, right? This again atomization process. I already mentioned about atomization a little while ago, okay? Where we talk about aerosols, right? So here, basically again, when this is aerosols, okay, very small droplets. So if we produce this type of droplets, very small, so we then use electric fields, okay, to melt the liquid at the tip of the nozzle, because we have to make this, because we are making some droplets, okay. That means this is in liquid form, right? And these small liquids, they dry, solidify, and they become nanoparticles, okay. So we have to send them through a very small nozzle, right? Very small hole, forced. So when we are talking about metals, we have to melt them, okay, and we do that just in front of the nozzle, make it into liquid form so that it will be forced out in the form of aerosols, okay. So this is a process, and finally we can typically use for platinum nanoparticles, and this process can actually give a high yielding 10 nanometer sized platinum nanoparticles, okay. So this is a very I could say popular way. We call it EHDA, or electrohydrodynamic atomization. Then this process called electrospinning. This again is used for mostly for polymers, okay, to make fibers, very thin fibers, nanometric size. We call them as nanofibers. So this is mainly for polymer samples. Sometimes if I get time, I can take you guys to IIT Guwahati. They have some electrospinning setups. Actually, they have some made by themselves. So there's a professor called Professor Utpal Bora. He happens to be a very good friend of mine. He actually designed one similar setup himself. Okay, so basically pulling out polymer fibers. You know what is a polymer? This is basically a molecule that is very long. That means it's a long carbon chain, right? It's a long carbon chain, and it sort of repeats. Okay, and the basic thing, that means we keep on cutting it, you get the same thing up to a level, and that level is called as a monomer. All right, that means a polymer is basically many monomers put together. All right, it's like many atoms put together, because if you try to break an atom, you won't get another atom, you'll simply get the subatomic particles, right? The protons, neutrons, electrons, all those things. So something very similar. If you cannot break down a monomer, if you break down a monomer, you will get carbon, hydrogen, different atoms. Something very similar. So electrospinning is a process for making polymer nanofibers. Now the others: liquid dynamic compaction, gas atomization, evaporation, and condensation. So there is a typically processes that is a lot about heat. Okay, so taking into the gaseous form or the liquid form, and then trying to convert that to nanoparticles. We won't spend too much time on this, but I will give you study materials. If you feel you want to go into details, you definitely can, and we can discuss also outside the class, because we won't waste the class time too much on going into details of this. Okay, so this is the EHDA process, the electrohydrodynamic atomization process. Okay, and you end up with particles like this, different shaped particles. And you see this plot here. This plot is actually here. This is the size of the particle. Now you can consider any size. We are saying that we take it across, like these are like disc shapes. This is the size. Okay, from here to here is the size, from here to here is the size. So this plot is size on the x-axis and the number of such particles on the y-axis. Now it's not that they are taking 1 billion particles to do these studies. Maybe saying said, okay, we do a study on 100 particles or 200 particles. We say 200 particles and we see how many numbers we are getting, all right, based on the size. Okay, and then you said at one size, okay, this is the particular size where we get the maximum particles, right? This is maximum here. So you say at this size range we are getting maximum, and this variation, okay, the spreading of the peak, this is called the peak, right? Spreading of the peak basically talks about the variation in the sizes. Okay, so when you have a broader peak like this, it means the particles are not very consistent, they are of different sizes. So this is typically how it is given. We call this as a particle size distribution plot. Okay, so we have another 5 minutes. It's a problem, okay? But anyway, that should not be a problem. The moment it stops, it stops. But again, please put in your attendance. But I see 18 here, including myself. So what I will do is I have to be particular on that. So I will keep a snapshot of these 18 participants, okay, in today's class. Because it's not correct also that you don't attend a class and you simply send in your attendance. No? That's not correct. What's the problem in attending the class? You learn something, right? But I'm okay with even one student. I only want interested people in the class. But I'm get surprised when students don't attend classes. I don't know what reason, but anyway. So we have half the number today. So, but even then, all of you who are here, you will send me your attendance in the WhatsApp group, and I'll compare with the list here today. Okay. Uh, and all right, let's continue till the class finishes off automatically. Okay. All right, let's go to the next slide. So these are continuations of the different thermal fabrication processes based on heat. All right. So I'll talk about already electrospinning, extrusion. All right. So I won't spend details on this because this might be too difficult for you to understand. But at least you should know some of the processes. Okay. As far as exams are concerned, I might ask you name a few top-down processes. All right. So you should be able to answer that. So this is dry ice sublimation. And this is another, I think I showed you the image. These are actually done by myself and my wife. Okay. We worked as a team to develop a machine that can make this type of nanostructures. Okay. And these are roughly about 100 nanometers in spacing. Okay. This is also a nanostructure. Fine. So this is a thin film made with holes like this. Okay. And this is on alumina. That means aluminium oxide. So what we do, we pick up a aluminium, put it here on the electrode. All right. And use electric fields to do the holes here. And these holes happen on the surface of the aluminium by oxidizing it. So aluminium oxidizes alumina, Al2O3. That's alumina. Okay. So we do this hole only in the oxide part because that is soft. The moment aluminum is converted to aluminum oxide, this is soft because that is not a metal, that is a semiconductor. Aluminium is a metal which is slightly brittle. Okay. So we cannot make these type of holes in aluminium, but we can do it in alumina, which is a semiconductor. Okay. So these are different techniques that have been adopted. This is another one which is called as dry ice sublimation. Okay, won't go into the details of this, but there's so many different techniques. Now we're talking about using thermal annealing, thermal energy for making nanoparticles, right? So these are high energy processes, right? Very, very high energy processes. I have used a couple of them when I was working in Sweden, okay? But these give you very, very nice particles and a lot of them. That means we get high yield and we get very, very consistent particles. That means most of the particles are on the same size and the same shape. Okay, RDchers, laser